Line Y1, learning task 1, we're going to start taking a look at our three-phase motors. And we're going to start out this one by taking a look at Squirrel Cage motor construction, because it's going to be the simplest of all of our three-phase types of motors to understand. And ultimately, we're going to go and combine components of the Squirrel Cage motor into all the rest of the three-phase types of motors that we're going to take a look at, whether wound rotor or synchronous or anything else. This is going to be a long segment. We're going to go from Y1, we're going to jump to V1, which are just going to be the titles of the different lines that we have. What we're going to look at is we're going to look at motors, then we're going to jump over to the associated controls, then we're going to jump back to the next type of motor, then we're going to take a look at its controls, etc. We're going to spend probably about 2 weeks in total in all of these sections. Why? Because it's a huge part of what we do, electrical motors. Now, some of the motors that we are going to cover over the next 2 weeks, you probably have never seen. Some of them you might never see, but the bulk of them are going to be used in common application. And before we even start talking about a motor, what we need to talk about is we need to talk about a couple of other things and some formulas that you need to have down and understood before we go through into the rest of what we have here. So we're going to go and, actually I'm just going to jump over to this one here. We're going to go and delete that picture, and let's start by talking about what a motor itself actually is. What a motor is, and I'm going to draw it over here as just a single line diagram, but what a motor is it is going to be a place where we are going to go and send electricity into windings. Those windings are then going to go and convert the electricity into magnetism. And then that magnetism is going to go and get picked up by another set of windings that is then going to go and create current through a load. Okay, we're drawing this just as a single line diagram. That current that we are going to go and create through the load is then going to go and use to go and create my rotation inside of the actual motor. So what we're looking at inside of a motor is we're looking at a bunch of different components. Let's just kind of take a look at what we're going to have. We're going to go and have our input side of the motor, the windings, the stator. We're going to talk about that in a minute, but those windings are a couple of different things simultaneously. The windings are going to go and be an inductor. The windings are also going to go and be the primary of a transformer. Okay, a motor is going to have inductive properties. It's also going to have transformational properties. Okay, it's going to be a transformer inside of itself. So my incoming windings are going to be an inductor. They're going to be a primary of a transformer. My secondary are also going to be made up of windings. It's going to go and be fewer turns usually. I'm just going to write that down there, windings. It's going to go and be fewer turns with higher current, but it's once again going to go and have some inductive properties, not loads of inductive properties, but some inductive properties, and it is going to go and be my secondary of a transformer. Because my motor is, once again, it is a rotating transformer. We send current into our primary. When we send current into our primary, we create magnetism. That magnetism goes across and cuts the secondary, which is then going to go and create current flow through that secondary itself. All of this is going to go and happen in the machine, which is going to ultimately give us rotation. Bunch of different formulas that you are going to need to know. You're going to have to know your formulas for inductance. L is equal to N squared mu A over top of little l. This is going to go and tell us how an inductor or anything that's inductive is physically made based upon the number of turns, the permeability of the core, the area of the core, all over top of the length of the core. So we're going to go and use this when we're looking at individual windings as a inductor that we're going to go and have. We're also going to go and have another formula that is going to be related to that one. And the other formula is going to go and be this one over here. E is equal to negative L delta I over top of delta T. Second year formulas. You guys are well familiar with this. This one here is going to go and be my counter EMF, and it's going to talk about the way that we build up voltage inside of a coil. That's this L over here, represents this coil, so the L transfers down to here. Anytime that we've got changing current over top of changing time, which is going to be an AC sine wave, changing current, changing time. Maximum change over here, minimum change over here, insofar as my current goes. We're talking about the change, not the absolute magnitude. We're going to need to use that one to go and deal with a bunch of our counter EMF that we are going to go and have inside of here. We're also going to go and use formulas that we have seen before, more so in DC, but we're going to go and apply them inside of AC. We're going to go and use this one over here, EG is equal to K phi N, and we're going to go and add on another section over that. We're going to go and add on a cos theta, which is going to be a power factor that we're going to have, but it's going to go and tell us about the amount of counter EMF that we are going to go and have inside of there. We are going to go and use good old Faraday's here. EG is equal to BLV. That one you should be familiar with, flux density, length, and velocity that we are going to go and have off of there. And we are going to go and have this other one that is going to be my T. Erase that one because it's too similar otherwise. T is torque is equal to my K phi N. And once again, we can apply a cosine to that one to go and figure out what our values of torque are. If you are not familiar with the way that an inductor works and how these formulas are applied to inductance, you should probably stop at this point and head back into it, or maybe after this video. We won't need it till after this video, but maybe after this video, before you start into the next section, go back and review what an inductor itself actually goes and does. It is going to go and oppose current, and it's going to oppose current by storing or using stored energy that's in the magnetic field surrounding the conductor. We're going to see that later on in a whole pile of these different motors, particularly, in some of the reluctance type of motors. It's going to become highly critical that you know these two formulas over here. Okay, enough about laying the groundwork over here. Let's start talking about this actual learning task 1 and the constructional features of our three-phase induction motors, or what we're commonly going to go and refer to as squirrel cage induction motors. First thing we're going to talk about is terminology, stator versus rotor. You should be quite familiar with that at this point, that anytime that we see the word stator, we're talking about the stationary component of our motor. And the beautiful thing about three-phase motors is they are so incredibly simple. What we will have is we are going to go and have the stator, which they show us over here. That stator is then going to go and have laminations that are going to be placed in here with slots so that we can go and place our windings inside of those. The laminations are there just so that we have fewer of our shred losses, skin effect, hysteresis, eddy current, dielectric, fewer of those associated AC losses, particularly the eddy current losses that we are going to go and have. And then we are going to go and take our windings, and we're going to go and have, A-phase windings, and we are going to go and have B-phase windings. I'm just going to go and have these things kind of overlapping here, and then we're going to go and have C-phase windings. And they're going to go and continue around in that same order, ABC, 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 all the way around. The beautiful thing is that these never move, which means that these leads, when they get brought out, I don't have to deal with any sort of brushes or slip rings or anything like that. My stator, I connect it physically onto physical incoming lines on these ones over here, and I don't have to worry about any sort of contact points, that have to rotate or anything like that. It says that the three-phase stator windings are made up of 3 single-phase windings placed 120 electrical degrees apart. By 120 electrical degrees apart, they just mean placed a third apart. Okay, there's not going to necessarily be only 3 windings. It could have 3 windings. It could have 6 windings. It's going to have some multiple of 3 because we need to have an even amount per phase inside of there. But it could be composed of many of them that are going to be just alternating around, or relatively few that are once again going to be alternating around. The next component we're going to talk about is going to go and be the rotor. And the rotor is an actual winding. It is going to be a cylindrical laminated core. So over here, they're going to go and take a shaft. They're going to go and mill out a bunch of these laminations. They're just going to be circular components that are going to go and have a keyway inside of them for the shaft, etc. And then that are going to be epoxy dipped. They're going to be made out of steel so that I can go and magnetize it, because I do want to go and hold on to magnetic flux. We want to attract magnetic flux in from the stator, hold it into the rotor, and then carry it through the rotor and release it back out to the stator on the next pull. We'll cover all that stuff later on. We want these to be made out of steel for 2 reasons. A, it's going to be a high permeability. Just write that down there. B, it's going to be low reluctance. Actually, I guess there's 3. Permeability is high. And C, electrical resistance is going to go and be high. We want this thing to be a high value of resistance, because what we're going to do inside of it is we are going to go and have some sort of a actual squirrel cage. We see this here, they call it the conductive ring. Well, what they're talking about is that inside of every rotor, we have got an assembly that is going to go and look like this. That's going to be made out of conductive types of materials, made out of aluminum or copper or brass or something like that that's going to be highly conductive. This gets milled in or placed into the actual lamination. So here I have the laminations. That means that going through these laminations, I'm going to go and have bars that are going to be going through here. Those are poorly drawn, but you get the idea that inside of there's going to be bars connecting this ring over here over to this ring over here. So that ultimately, if we would cut away all the last steel laminations, we would be left with something that is going to go and look like that. Now, if it's on a large machine, they're going to go and take punch outs, and then they're going to go and drive rods through these, and then they're going to go and short those rods across here. They call this the shorting ring at the far end. Usually these are not going to be straight through as well. Usually they're going to be slightly skewed or on a little bit of an angle. And this just means that we're going to get a smoother operation out of it. It kind of jumps from one phase over into the next phase a little bit more smoothly, because the tip of that bar, because it's slightly off angle, is going to be moving through into the next magnetic field and ready to be picked up by it. In smaller motors, what we will do is we will go and cast these things. So they're going to go and take all these laminations, they place the laminations inside of a mold, and then they go and cast in the aluminum. And over here you can see the cutaway of that we've got once again the shorting ring that would go all the way around, and through these slots the aluminum just pours through. And then they go and use the aluminum extrusions off of here, where it's poured into there. They go and cast them into these shapes over here, so that we're going to have a centrifugal fan on it as well, just to be used to go and cool down the windings. This is it for our rotor, or for our secondary of our transformer. Once again, you guys remember that I've said right at the very beginning, these things are going to go and be a transformer, which needs to go and have a primary. This is going to be the primary of my transformer. If I were to look at this as far as transformer action, I'm just going to say TX primary. The stator is going to act as that. The squirrel cage is going to go and act as my secondary on there, because if I take a look at this, I see that I have got complete paths that current can go and flow. We're going to go and see complete paths down one bar, up another bar, and across like that, ultimately inside of this rotor. That's going to get covered inside of the theory, so don't worry about it for now. Just note that there is a complete path, and therefore this thing could be termed as a winding. You see that it is going to go and have few turns. Really, it's only got one bar going through here. And that it's going to go and have low resistance. Few turns means high current. Low resistance, because this thing is going to be made out of aluminum or copper, which means we're going to get a lot of current that is going to actually flow through these bars. These bars are not here for mechanical support. These bars are here for conducting current, and large amounts of current. Same with these ones over here. We're going to go and have current that is going to go and travel through these bars, through the shorting ring, go down through the next one, and then it's going to be able to go and loop back around. Large amounts of current flowing through low amounts of turns. This is going to go and be my transformer secondary that we are going to go and have. The other reason that we do have the steel inside the core, we talked about the fact that we want to have the high permeability and the low reluctance. Those are magnetic properties, but we're also going to want to have a fairly high value of resistance, because the actual aluminum is not going to be insulated from the steel. But we know that our current is going to take the path of least resistance, which means it's going to go through the aluminum sections primarily. A little bit can go through the steel, but not a lot, because the laminations are going to go and slow it down, and it just doesn't want to go and travel through that high resistance path. That's going to be the basic assembly of these. Obviously, on either end of the motor, we're going to have our end bells, which are going to go and be the components that are going to hold the shaft in the center. Those are going to go and support our bearings and other components like that. We're going to need to go and have the motor termination box off of these things as well. All of those are just kind of assorted ones, but they don't make much difference to our operation. The enclosure, how this motor is going to be built, is going to make a difference, though, to the way that it is going to go and cool. Let's just talk about this thing. Right now, if I see this enclosure over here, I've got this main frame that I'm going to be mounting everything onto. That frame is usually going to be a solid piece of steel. We're going to go and want to have something that is going to go and carry magnetic lines, obviously on the inside. Sometimes if these are aluminum on the outside, then there will be steel going around on the inside to complete those paths. But what we will have is then we have to place these end bells that are going to go and seal these things off. We're going to have varying amounts of sealing. If I don't seal very much, I'm going to get good airflow, which is going to be good for cooling, but obviously it's not going to be great for a lot of my environments. If I've got dust or anything like that, or corrosives, or anything that is going to be granular, that's going to go and grind it down, I might not want to go and have that open type of machine. I'd probably want to have a closed type of machine. Inside of your binders over here, they go through a whole pile of different types of enclosures. These are going to be NEMA designations. And the NEMA designations are going to be two-part designations. What we are going to see off of them is going to be how it's protected or if it's protected. So the first part is going to be protection. The second part is going to go and be protection. The second part over here is going to go and be cooling, how this thing is cooled. And we don't have to have something. This thing could be skipped. If there's no protection, we wouldn't have to place anything inside there. If there's no cooling, we wouldn't have to place anything inside there. But you're going to go and see different types that are going to go and be placed inside there. The first one that we are going to go and have is going to be open types of machines. Open types of machines do not mean that they're going to be sitting wide open. It just means that there's going to go and be some places for us to go and have air cooling, that's going to flow all the way through. The first one that they talk about is the drip-proof machine. Now, the first thing that we should talk about is that this thing is actually going to go and be called ODP, Open Drip-Proof Machine. It's one of our more common ones that we are going to have. All that it means is that the openings are going to be down low. The end bells are usually going to be sealed all the way across the top. So if any water drips onto it, it's going to run down past here, and then it's just going to drip away. It's not going to go and get inside of the motor itself. But a drip-proof machine is only good to go and block anything that is vertically dripping down on it. That's all it can go and guard from. Anything that is splashing up and into it is not going to be able to be blocked out of a drip-proof type of machine. If I want to increase the guarding, I'm then going to go to a splash-proof machine, which is going to be open on the bottom, but then it's going to go and have as well another shield that's going to go over top of it. That is then going to, prevent us from being able to get back spray into it, etc. Then they go through semi-guarded, guarded, drip-proof guarded machines, open externally ventilated, and open pipe ventilated machines. Open externally ventilated machines and pipe ventilated machines are going to be used in certain industries, particularly the pipe ventilated ones, where I might have a process that is going to be, corrosive, or it's going to go and create dust that's going to be a wearing type of dust, like rock type of dust that would grind down surfaces. I don't want to necessarily introduce those inside of my machines because it's going to lead to premature wear. So I'll take filtered air from the outside, and in some cases, I will actually go and pipe air through my motor to go and cool that motor off. It's not going to be as common for us to go and pipe stuff in as it is for us to go and close our machine. We're going to talk about another common designation over here. The first one is the TENV, totally enclosed. The protection, non-ventilated. We have no external types of ventilation that this thing is going to go and have. TENV are going to be a completely sealed unit. We use them pretty much in any type of application. They will get hot. You're going to have really good windings inside of them because they don't have any sort of ventilation. If you put these inside of an area where you got high ambience, they will cook faster than others because everything is going to be trapped on the inside. And if you go to too rapid of a temperature rise inside of these, you can also have other problems where you're going to go and end up with ruptures in the casing, blowouts in the bearings, etc., because you're just going to increase the heat inside, which is going to increase the pressure, which is going to go and give you your mechanical issues. Oftentimes, it's in the TENV, which is just going to go and have two smooth end bells. What we're going to go and see is we're going to have a TEFC, totally enclosed fan cool. And what the TEFC has, if I can just draw this here, who knows? Some days I can draw, some days I can't. I'm going to go and have the motor, and then around the back end of the motor, there's going to be another shield that's going to be stood off from the motor, just, maybe about a 1/4 inch or something like that. That shield at the back end of the motor is going to go and have a small shaft extension that's going to have a centrifugal fan, and it is going to go and pull air in to that centrifugal fan, and then it's going to force it up and out like that over top of the motor to go and cool that motor down. We're just using forced air to go and run that one down. TFC, you got to just make sure that there is path for airflow and that airflow is not trapped inside of a box. If you build a machine and then you place a totally enclosed fan-cooled motor inside of a box and then seal that box off, it's just going to heat up all the air inside there and you're not really gaining a whole lot out of that thing. Explosion proof, dust proof, ignition proof, waterproof. There's a bunch more that are less commonly used. We do have totally enclosed pipe ventilated. We do have water cooled, where we're going to have a water jacket on them. Usually it's going to be water with glycol inside of it. It's like an antifreeze type of thing that allows us to be more thermally dense. A bunch more that we're going to go and have over. The very last one that's a common one, so we got the TNV, the TFC. The last one that we are going to go and have that's commonly used is the TEAO. Totally enclosed air over. This is going to be specifically used for fans. It's a very common motor because we have got a lot of fans to go and move air, ventilate, transfer dust, loose stock, etc. around industrial. But if you do pick up a motor and it's a TEAO, that motor is only designed to go onto a large fan. What we have over here, the TFC. For the TEAO, totally enclosed air over, what you have to imagine with that is that it's going to be connected onto actual large fan blades sitting inside of a housing. So we'll have some sort of a housing, and this thing is going to get bracketed out to the center of that. It is designed for the bulk transfer of air over top. If you take a TEAO and you replace TENV, TEFC, or any other with that totally enclosed air over is going to overheat and burn out really rapidly. So just use them inside of the proper applications. Encapsulated or sealed windings are also going to be used sometimes, but they're going to be more expensive. It's where they're going to take the windings and they're going to go and epoxy encapsulate them. They're going to pour stuff around them that's going to go and prevent moisture, going to prevent corrosive, it's going to prevent gases. In some cases, it's even going to go and give us explosion-proof types of properties. They're really going to be only a specialized type that you're going to use when you've got heavy, dirty, and dangerous types of industry inside of them. Let's talk about nameplate information now. First of all, let's talk about the one extremely important thing that is missing off of this nameplate over here. If you want a challenge, pause the video for about 30 seconds. Take a look around, see if you see the one thing that is highly critical that is missing off of this. For those of you that aren't up for a challenge or just bored or whatever, what you should note is that there is no certification mark on here. Okay, there has to be something somewhere. So we'll just place one on here ourselves. We will do a CSA stamp that we're going to place onto this thing. If your motor, if you're looking at the nameplate and if there is no certification off of it, don't even look any further at that thing. Get rid of it. Get yourself a proper motor. By the way, this CE thing that you see on some motors, that is not a Canadian certification. That is going to be a European certification. It means it's a certified component. It can be recognized, but it needs to go through external regulatory bodies. So if you see that CE on there, do not rely on that one. It's not recognized here in British Columbia as being actual safety. So we'll start with our nameplate over here, nameplate information. This is going to be typical stuff. Now, for us to go and have a certified motor underneath the Canadian Electrical Code, and particularly here in British Columbia, it is going to go and have to go and pass some approvals. And one of those sets of approvals is that they want to know and have what the manufacturer's name and the catalog number is going to go and be. They need to have some trackability. It's part of the process of certification is saying who built this and where am I going to find the information, or what's the name that I'm going to use to look up the information in case there is some sort of fault. The whole idea is that we're going to have ready information available for us. From there, we're going to go down and we're going to take a look at frame. Frame is going to go and give us standardized mounting patterns. Frame sizes are going to go and be NEMA standards, and they're going to go and tell us things like how far apart the motor feet bolt patterns are going to go and be. How far from the center of the motor feet is it going to be up to my shaft? All of these distances, etc., are going to be based off of that frame. There's only going to be a limited number of frame sizes that are available. But inside of those frame sizes, we're going to have multiple horsepower. So this 182T, we're going to go and have our 3 horses. We're going to have 2 horses. We're going to have 5 horses that are all going to be available inside of it. What I need to do is I need to make sure that I'm selecting not only the right horsepower, but also the frame size. Horsepower is going to go and tell us what this thing is rated for to go and deliver. This is going to go and be the horsepower that is going to be at the shaft. Okay, it is not going to be what we have ahead of losses. This is going to be after losses. So we're actually going to need more than this 3 horsepower on the input because we have a couple of losses, windage, frictions, bearings, heat losses that are going to be coming off of this motor itself. The horsepower, though, we're going to use that for sizing to the load, and then the horsepower does also have this really, really cool thing called the service factor. We've talked about it earlier this year, but you have to know what this is. Service factor is going to go and be a multiplier that is going to go and tell us how many horsepower we can actually put out continuously from this motor before the motor itself is going to go and cook off. Let me just pull up the calculator over here. We know that we have got a 3 horsepower motor with a 1.15 service factor. That's what we see over here. So 3 times 1.15 gets me out to 3.45. So basically this motor, if I went down to the nuts and bolts of it, is a 3.45 horsepower. Now I'm not going to use that to size the load. I size to the 3 horsepower. This service factor over here is just going to be the manufacturer's safety that they're building into that, so that if you come back with a burnt out motor, they're going to say you're an idiot because this motor was designed to be used on a system with a demand of 3 horsepower, but clearly if you burnt it out, you were using it on a system that had more than 3.45 horsepower of demand. I'm not going to warranty that, you pay for it. And that's what it's going to come back to you for. So that service factor, the higher the service factor, the more that you can go and overload that motor. Time ratings, when given on them, and they're not always going to be given, are going to be either continuous or short time. If there is no time rating, it has to be assumed that this thing can go and operate continuously. If it does have a time rating, it's going to be 5, 10, 15, etc. And it's going to be designated amounts of time on, followed by time that is going to go and be off. Maximum ambient temperature, and then my insulation class are going to be 2 related things that we are going to have over here. Maximum ambient temperature is going to be where I'm supposed to be placing this thing in. If it's going to be maximum of 40, I don't want to place this thing necessarily up high in the rafters of a boiler room, because that thing is going to be in like a 50, maybe 60 degree or something like that. Make sure that where you're mounting it is not going to be hotter than what that maximum ambient temperature is. And then the insulation class that we are going to have inside of there is going to go and be just a rating of how strong that insulation itself actually is. And we go through a bunch of different classes. They're listed inside of your book there, but all these classes are going to go and follow the same layout, where we are going to go and have 3 separate things that we are going to have. We are going to go and have base temperature. Then we are going to go and have the amount that the temperature can go and rise. And then the amount that we can rise above that for a hot spot, which is just going to be a small spot, you know, on there, any point that's going to be the absolute highest value of heat that we are going to go and have. And what this is going to go and tell us is basically how hot this motor is going to get during operation as well. We're going to go and have to use these later on when we are trying to go and size all of our motors for, you know, which type of, which temperature am I going to go and use for my conductors coming in. Because this really tells me, this insulation class tells me what my internal temp could possibly be, okay? Internal temp. Now you got to think that if that's my internal temp is going to be off of this class B, that internal temperature is then going to get transmitted to the outside, because I've got copper conductors. Copper carries heat very, very well. If you don't believe me, you know, take a piece of copper wire, heat one end up with a lighter, see how long you can hold on to the other end before it's going to burn your fingers. Not very long, because it's thermally dense. So I'm going to go and have these A, B, C, D, E, F, G, and H. Of those, we're really only going to go and see A, B, F, and H as being our normal ones. Once again, these are going to be ratings that you can look up online. We also have got a table inside of our electrical code that gives us. Now, before we go into these tables, I just want to go and point out that what the table has is going to, inside of the Canadian Electrical Code, is going to be different than what the actual insulation rating itself is. Because this insulation rating that we're looking at is what we have inside. It's our internal temperature of the motor. And the Canadian Electrical Code recognizes that as it leaves the motor on the conductor, there will be a drop in temp between what my internal temp is to what it is going to be inside of that motor connection box. So let's just quickly go through these 4 different ones that we have. Class A is going to go and get me to a maximum point that is never going to be more than 105 degrees inside of my motor. And what it is it's going to go and have a base temperature of 40 degrees that we are going to go and have, and they're all going to have the same 40 degree base. And then over top of that 40 degrees, I'm allowed to go an additional 55 degrees that I can go and have as a regular rise, which is going to go and take me all the way up to 95. And then on top of that 95, I can have 1 or 2, spots. Any individual spots inside the motor that cannot be more than 10 degrees more than that, getting me all the way up to this 105 degrees that I'm going to go and have for an internal temp. And all the rest of these are going to be done the same way. You know, my A is going to be 105, my B is going to be 130. We get a greater rise. My F is going to be 155. Once again, we're going to get a greater rise. And then my H, which is going to be the strongest one over here, is going to go and get a greater rise. Now, it is going to go and still give us, because each of these is going to go and have different values of temperatures, it is still going to go and affect my connection that I'm going to have. 4006, which we talked about this year, talks about temperature terminal ratings and the fact that our loads are not allowed to overheat our wires. So if the inside, we're going to go back to a class A over here, gets all the way up to 105 degrees at a maximum hot spot, 95 degrees at a regular spot, that would mean that we would not want to go any higher than that on our absolute output. So we go and take a look at our Canadian Electrical Code, Table 37 of your Canadian Electrical Code. There's a whole pile of tables inside of the code that deal with this stuff, gives us these ratings. I want you to compare A, B, F, and H inside of here compared with your binder. First of all, you'll note that the enclosure is rated. Inside of here, this one says everything except for totally enclosed non-ventilated. This one over here is only totally enclosed non-ventilated. Inside of a totally enclosed non-ventilated motor, obviously it's going to get hotter. There's no place for that heat to go and escape, so I'm going to go and have higher ratings. Any other type of motor, it's going to be able to be cooled more effectively in most cases, so we're allowed to go to lower ratings. What this tells us, this table over here, is it tells us that if I've got an A insulation class motor, where the internal of the motor is going to get up to 105 degrees, I need to make sure that the external conductors that I connect to it are going to go and be rated for at least 75 degrees. And if I've got, a B type of motor, then I'm going to have to make sure that, once again, it's good for 75 degrees. It gets up to 130 inside, but I'm allowed to connect with 75 degrees on the outside of the motor. On F, that one gets all the way up to 155 degrees. I can go and connect to with 90 degree conductors. This is going to be most of your techs and other cables like that. And then on H, I'm going to need to go and have 110 degree conductors. And this is for, once again, everything except the totally enclosed non-ventilated. Totally enclosed non-ventilated just has the change that we're going to have 90 at the B and then 110 from that point onward. Insulation class is going to be important for us just to make sure that we don't overheat our conductors that we have inside of there. Okay, moving past the insulation class, then that's going to go and give us another set of associated components that we're going to go and have. Let me just get an eraser out here. We'll get rid of the bulk of this. Next set of associated components that I'm going to go and have is going to go and be frequency and RPM that are going to be rated together. Cycles is often how they're going to go and state frequency. It's just an older method that has stuck in the motor industry. RPM is going to be how fast that motor is going to go and speed up based upon that. And from that RPM, we're going to find out that later on, I can take this and I can go and say, hey, what's the closest, 60 multiple? I know that it's going to be 1800 RPM. And from the 1800 RPM, I can then go and infer things like the number of poles, etc. This is going to be, how fast the magnetic field is spinning. This is how fast the rotor is spinning, trying to catch up to it. We'll cover that stuff later on, but it, allows me to go and make a relatively decent jump from one to the other. They are directly related, meaning that if my frequency would change, my RPM would go and change as well. This can be good if I'm going to go and run this thing on a variable frequency drive. However, if it's run on a variable frequency drive, what I want to see is that this thing is going to be rated for, it's called inverter duty. And it should be rated on there. If it doesn't say inverter duty or inverter drive motor or something like that, don't put it on a variable frequency drive because it's not designed for that variable frequency drive. It might last, but it might not last as well, and it could go up in flames or something like that. So frequency and my RPM are going to be inherently tied together, and if I change my frequency through use of a variable frequency drive, I'm going to go and change that RPM that I'm going to have as well. Volts, that'll be our next one. Volts is going to be a dual rating, and we're going to go and see dual ratings that are going to go and happen because we have got two different ways that we can go and connect over here. If we take a look, there will be a drawing, sometimes on the nameplate, other times inside the motor terminal box on a sticker in the back of the box or something like that. That is going to go and tell us how we can connect this thing for either a lower voltage or how we can go and connect this thing for a higher voltage. And we are going to go and use these ratings for the volts and for the FLA, or the full load current, or the amps, together with these drawings to go and connect to it. So if I had this thing that I had a 230 volt three-phase line, I would go and make this connection. 1 and 7 would go to one of my lines, 2 and 8 would go to another line, 3 and 9 would go to another line, and then 4, this one here, it's missing a number 5, but it should be 4, 5, and 6, would be connected together. Same as if I was going to go to the higher voltage, I would go and, use this 4 to 7, 5 to 8, 6 to 9, and then a single line out to 3, single line out to 2, and a single line out to number 1, like that. My amps are going to be directly related with the slash rating. If it's the lower value of volts, it's going to be the higher value of amps. So you can just go and, take 230 times 9.9. This is going to go and give you your VA. Guess what? If you have got your VA and if you have got your horsepower, which is going to be watts, you can also figure out things like your power factor of that motor, etc. Okay, that's going to be my volts and my amps. We're going to cover all these connections later on. So once again, don't worry about what the connections themselves are. Just understand that for now, if you're doing any connections, just connect them as to those drawings and everything is going to go and be correct. Code letter for locked rotor kVA. This is a cool one as well. This is going to go and help you deal with your inrush. Okay, it's really going to go and tell you how much this thing is going to go and give you for inrush on the input, and it's going to be an alphabetical letter that is going to start all the way at A, and then it's going to go down through the alphabet. We'll stop at L maybe and go down through a little bit further all the way over to the letter U. It doesn't have all the letters of the alphabet. It's only got what is it, 20 maybe 22-ish steps in total or something like that. I don't know, I can't remember. I haven't memorized the whole table, but I do know where these things break down at. Basically, A breaks down at a value of pi, or 3.14. I'm going to go over what the number means. L is going to go and be a 10, and U is going to go and be no more than 22. What this means is that it is a multiplier. It's going to be my amount of inrush that I'm going to go and have per horsepower. So if I've got an A type of motor, that A type of motor, let's cross this out, we'll make this an A. If I've got an A type of motor, that means that when I've got the motor at a standstill, that's what a locked rotor is, it's standing still, that would mean that for every horsepower on here, I've actually got 3.14 horsepower of inrush that I'm going to go and have. So I can go and say that, I'm going to take this amps that I'm going to have over here, and I can go and multiply it by 3 times. So for this one here, at the very peak, I'm going to have, up to 3 times 10, so about 30 amps of inrush when I try to start this motor out. If I go to a L is going to be mid-range. It is going to go and be at 10 times. Okay, so I'm going to have about 100 amps of inrush, just for a split second as this thing is starting up, and it doesn't last very long. And if I go all the way up to a U type of rating over here, then I'm going to go and have up to 22 times. It's going to be my horsepower per kVA that I'm going to have here, or inrush current per kVA. 22 times, this 10 amps, so this one would be almost up to 220. It's going to be really a measure of how good of a motor builder this manufacturer is. If this is from a good motor manufacturer, like a Baldo or something like that, that's recognized, WEG, some of these guys that just throw out motors, day in, day out, they're going to usually have pretty decent locked rotor kVAs. But if it's going to be a crappy, low tolerance, cheap motor, then it is going to go and have a higher locked kVA code. Once I get it running, I can have all sorts of different motors. I can have A's, I can have K's, I can have U's that all give me 9.9 amps when they're running, but they're all going to give me different amounts of inrush during that. And that inrush is really going to go and determine a lot of the sizing and how it's going to affect other loads, right? If I get a 200 amp inrush, everything else around is going to go and brown out as I start it out. Okay, design letter. Design letter is going to go and talk about the resistance of the rotor, or how good of a rotor I have. We're going to find out later on that my design letter is going to go and tell me a lot of stuff about startup torque versus running torque, and where those things are going to go and be peaking at. That it is all going to be based upon the resistance of the rotor. And in some cases, particularly with our wound rotor motors, we can go and adjust what that resistance is going to go and be. Designation of terminals, they talk about that down over here. We're going to have terminals that are going to be designated so we can go and make these connections. Evidence of approval, we talked about that at the very beginning. That should be the very first thing that we are looking for, not the last thing that we are looking for. What's the point of doing all the rest of the analysis if you aren't able to go and utilize this thing? And then last of all, they have got this, CSA energy efficiency labels, and this is just motors that were manufactured after 1993. So before, some of you guys' birth. They just had to go and bear this CSA energy efficiency label to show that they were efficient enough that we weren't going to be wasting a lot of power. Why is BC so big on energy efficiency? Well, it's because we have got a ton of power, but we also want to go and sell a ton of power down and out to the United States if we can. So the more efficiency that we can save here as a province, the more that we can sell for big dollars down to the United States. That's a copy of what one of these energy efficiency labels is going to go and look at. Okay, that is it for our intro to these. Once again, now, if you do not remember all of these formulas, go back into your second year inductance and go through, just what these L and the E, the counter EMF, the buildup of counter EMF inside stuff, etc. Make sure you review that before you move on to the next components, because it's just going to be more difficult if you don't have that basis, that grounding.